Okay, so in this, oh, wait a minute, why are there cows? I just want to keep your education moving along. Here we go. So in this presentation, we're going to talk about calculating heat. And I don't mean an old movie by, well, with Al Pacino, Robert De Niro, and Val Kilmer, but we're going to see what we're talking about momentarily. So there is a physical property of matter called the specific heat capacity, which is defined by the amount of heat or energy required to raise the temperature of 1 gram of that material by 1 degree C. So it's a number, basically tells you how much heat that material can hold or how much energy you have to put into that material to heat it up or how much energy is released when it cools down. So this is an interesting graph related to the potato and aluminum foil. Down the bottom, we have our independent variable heat added. So as we add heat, we expect the temperature to go up. But as we add heat to water, we have a very slow slope. And as we add heat to aluminum, we have a steep slope. So it takes less heat to raise the temperature of aluminum than it does to raise the temperature of water. So the slope of this will tell you something about the heat capacity of the material. It's also dependent on the mass, but let's assume we have the same mass of aluminum and the same mass of water here. So this is just a concept that we're trying to get across. What happens when we cool things down? Well, heat is released. The only way I could do that with this graph. Okay, so maybe if we flip it around, as you cool something down and you go from a higher temperature to a lower temperature, um, we can see that this heat is actually going to be removed. So as we cool, let's say, water down, or we cool aluminum foil down, right, um, uh, for the same amount of heat lost, we're going to get a much bigger temperature drop for aluminum than we are going to get for water. Specific heat is represented by the constant C, sometimes also C sub P, so you might see this in your book. I don't like C because C is usually the speed of light, but we're just going to go with that. And it's different for every material. It's actually different for the state that you're in or the phase that you're in. So for pure water, we're looking at 4.19, and the units are joules per gram degree Celsius. So how many joules does it take to heat up 1 gram for 1 degree Celsius? Steam, a little easier to heat up than water. Ice, a little easier to heat up than water. And here's some other numbers as well. When we start talking about metals, these numbers are going to be very low. Like I believe for copper, the specific heat is like zero point 0.3 or zero point 0.4. So about 10 times less heat has to be added for a metal like copper than for water. But these are numbers that we're going to use in an equation. So the formula that we're going to use to calculate the amount of heat to raise the temperature of a material and a specific mass of the material. So this C is going to tell me what material I'm talking about. If it's water, I'm going to use 4.18. If it's copper, I'm going to use like 0.3 or zero point 0.4. So this is per material. This is how many grams we have, and this is the change in temperature of that material. Will tell us how much heat. And if we look at this equation, we can see that if the mass goes up, right? If this mass goes up, the amount of heat is going to go up. If the change in temperature goes up, I need more heat for that too. So you can start logically putting together the values in this equation. I wanted to go back to the phase diagrams. That equation is only valid when we have only one state or one type of material. So that equation is only going to be valid for this part of the heating curve, or this part of the heating curve, or this part of the heating curve. That equation is not valid when we have a state change or a phase change. That equation does not work here. We're going to look at another way to calculate the heat for that. So we can only use MC delta T where the temperature is actually changing. Here the temperature is changing. Here the temperature is changing. Here the temperature is changing. We can't use MC delta T where there's no temperature change. Here's a sample problem for you. How much heat does it take to raise the temperature of 100 grams of water from 30 degrees to 100 degrees Celsius? So we're going from somewhere around room temperature to boiling, a little warmer than room temperature to boiling. The C of water is 4.186. We have this equation that I just put on the previous slide, and we just put in the numbers that we know with the units. And right, so the units should cancel out. So 100 grams times 4.186 joules per gram degree C. And then here's my delta T. So delta means final minus initial, right? So T final is 100 and T initial is 30, T initial. So delta means change. So this is my delta T. And you can look at the problem and see that it's 70 degrees. Sometimes it's negative 70, right? If something's cooling off, then the heat will turn out to be negative. And that's okay. That just means we're removing heat from the material. This C is going to cancel out with those C's too. So that's our equation. It's also referred to as MCAT because sometimes this little delta looks like an A. So you can hear people refer to this as MCAT or MC delta T. Great. Okay, so what happens when we are in this section or this section when there's no heat change? I'm sorry, no temperature change. You almost caught me in an error in the back of the room there, but John wasn't paying attention. He almost had me. So anyway, so when we don't have a temperature change, when we only have a phase change, we're going from solid to liquid or liquid to gas or gas to liquid, liquid to solid. What do we have to do? Because there's no delta T. Let's take a look. So let's talk about this new concept called the heat of fusion. And it's the amount of energy that you need to melt something or to freeze something, the other way around, the amount that's given off when you freeze something. So if we're melting something, if we're going from a solid to a liquid, we use a variable or a property called the heat of fusion. So how much energy does it take to change 1 mole of a material from solid to liquid? And for water, it's 6.02 kilojoules, so 6.02 thousand joules or 6,020 joules. Lizzie, check my math on that. All right, thanks. And so it's a physical constant for that material, heat of fusion. The heat required to melt an amount of a substance is going to be N, the number of moles times the heat of fusion. So this heat of fusion is the energy per mole, and I just multiply that by the number of moles, and I get the amount of heat. For water, that's going to happen at 0 degrees. Everything is going to be at constant temperature, so there's no delta T. This is, sometimes you can look in the problems to see if it says ice or if it's freezing or melting. And that's this relationship. It's when everything's frozen. So if you have any anger right now, if you have any like pent up frustrations about chemistry, I'm just going to say, let it go, da da dee da da dee da da dee. That's all I got right now. It's only Wednesday. What is that energy actually doing? It's going from taking this solid structure and breaking up the intramolecular bonds, the ones between the molecules, and kind of separating them a little and turning it into a liquid. Again, we're not raising temperature here. No delta T. No delta T. But there is something going on. So the energy is just going into doing that, to changing the structure. So how does this work? How does this work mathematically? You may get a question that says how much heat is absorbed when 10 grams of ice melts at 0 degrees. The heat absorbed is going to be the moles of the substance, times the heat of fusion of that substance. So I got to go from 10 grams to 10 grams to moles. I know water is 18 grams per mole because it's 16 for oxygen and 2 hydrogens makes 2, so 16 and 2 is 18. So I just take 10 grams times 18 grams per mole. This will give me how many moles I have, and I multiply that by 6.02, which is a constant from the slide. And this is well, what is that? How did I get from kilojoules to joules over here? Well, I don't really know. Oh, I remember how I did that. And when I multiply this all out, I wind up getting 3.344 kilojoules, and I just converted it to joules. So if you don't like that, you can write 3.344 kilojoules. Where did that energy go? It went to taking that solid structure and making it kind of wee liquid structure, right? Wee, all right. So it took that solid and went, there we go. Patent pending on that demonstration. Okay, so what happens when we're going from, let's say, a liquid to a gas? If we're boiling something, the formula is very similar. The amount of heat required to boil something is going to be the number of moles times another constant, heat of vaporization. Wow, that got stuck in there. In this case, we have liquid and gas present as we slowly convert the liquid to a gas. You can look at words in the problem like boiling or steam. If we're going the other way, we're condensing. So we're taking the gas and we're condensing it into a liquid. For water, this happens at 100 degrees. Again, constant temperature here, so no MC delta T, just NHV. So what is the heat of vaporization? It's the amount of energy required to boil a gram of a material or convert it from liquid to a gas at its boiling point. The variables HV, and for water, 40.6 kilojoules per mole. So higher than that higher than the going from solid to liquid, going from liquid to gas takes a lot more energy. Similar type of problem, how much energy does it take to vaporize 10 grams of water? Oops, this is supposed to be an N. Thank you in the back. Way to go, Patrick, paying attention back there. All right, so Q, I've got to convert to moles. So here's my converting water to moles. Again, right, 10 grams over 18 times that 40.6 kilojoules per mole equals 22.6 kilojoules. It takes a lot more energy to go from liquid to gas than from gas to liquid. Well, why do you think that is? Pause. You guys can talk amongst yourselves. Check your phones. Who knows? Is it 2 o'clock yet? Do we get to put the chairs up? Got to keep working. The particles are really spreading out and they're breaking that intramolecular bond. So these guys that are kind of linked together here, these are not just getting looser, like when we went from solid to liquid, we went looser. Now we're going from loose to totally breaking free, right? Totally breaking apart from each other. Lots of kinetic energy. So we call that the latent heat or the heat of vaporization, and that takes a lot of energy to do that. And you can see that I grabbed this picture from a British site because they like to add extra U's because, I don't know, they got nothing else to do with their time but add U's to their letters, right? Color, vapor, I don't know what else. Send them to me in a text. I am me. Instant chat, whatever you want to do. Tell me where the U's are. And don't say the U's are in the shepherd's field. I heard that pun, Benton. Good one. All right, so here's a sample problem. How much energy do I need to add to 72 grams of ice to melt it? The heat of fusion of ice is 6.02 kilojoules per mole. I'll give you a second to try and use what we did before to solve this problem. I'll wait. Pause the video. I think I'll have some tea. What does my cup say? Grandpa's, dad's without the rules. That's right. Okay, so how do we solve this? There's no temperature change. I'm going to take 72 grams of ice and I'm going to convert it at 18 grams per mole. That's 4 moles of ice. I can use this formula, 4 moles times 6 kilojoules per mole is the heat of fusion. and I get 28 kilojoules. Okay, so let's summarize everything. When we have a phase change, we can either use the NHF or we can use NHV depending if we're melting or if we are boiling. Equations are very similar. We have the number of moles and we have two constants that go along with that material. So all in all, we have three equations. Oh, sorry for the capitalized C. We have MC delta T when there's a temperature change. And we have these other two guys only when there's a phase change. So you need to look at the heating curve or think about what's going on when you want to solve the problem. Look for hints in the problem, right? Look for hints in the text to see if the phase change is happening or if we're going from solid to liquid and then hotter and hotter, for example. Here's our heating curve again, and this is a nice little picture. So if we're in this phase, it's MC delta T for the solid. Here, N times heat of fusion, so number of moles. Here, M, C delta T, where we're looking at the liquid heat capacity. N, HV, where we're just boiling. And then M, C of gas delta T, where we're heating up the gas. So finally, again, anytime we have a slope or anytime we're changing the temperature, we use this type of equation. These are just some words that you can look at in the problems if you're having trouble dissecting the word problems. If the temperature is changing, if it's increasing or decreasing, we're going to have to use MC delta T. Okay, so good luck solving the problems. Take a look in the book. There's other videos that I'm going to post, and there's 3 separate worksheets for you to try. Let me know if you have any trouble. And keep on smiling. And anyway, hope you have a nice week, and check in for the next videos later. Peace out. Why do I say peace out? I'm too old for that. I say goodbye, you youngsters.